On July 16th, 2026, Hugging Face published an unusual security disclosure. Someone had breached their production infrastructure, executed code on a data processing worker, harvested credentials, and moved across multiple internal clusters over the course of a weekend. But one detail stood out. According to Hugging Face, the attack appeared to be carried out end to end by an autonomous AI agent with thousands of individual actions and no human operator directing them. They also admitted that they didn't know which model was responsible. And 5 days later, OpenAI published a blog post that answered the question. It was actually them. So it was not an attacker using the OpenAI API, but their own models running inside an internal security evaluation. And these models escaped the evaluation sandbox, reached the public internet, and targeted Hugging Face in an attempt to steal the benchmark's answer key. Today, we're going to reconstruct that entire chain from the benchmark that started all of this to the sandbox escape to the attack itself. I've used official communication from Hugging Face and OpenAI as the baseline research materials and distilled all of the publicly available information into these diagrams we're about to see. It's going to be a highly visual video, so I'd like you to stick around till the end if you want to understand how the entire attack chain works. So why were OpenAI's models trying to steal an answer key in the first place? Because they were taking an exam. The benchmark is called Exploit-Gym. Unlike most cybersecurity benchmarks, it doesn't ask a model to explain a vulnerability. It hands the model vulnerable code or build materials and asks it to produce a working exploit. The original paper introduced 898 exploitation tasks. The curated benchmark used here contains 869. Grading is simple. Either the exploit works or it doesn't. And like any benchmark, Exploit-Gym also has reference solutions. Somewhere inside the evaluation environment is a complete answer key. Now, OpenAI wanted to measure the model's maximum capability. To do that, they disabled the production safety classifiers that normally refuse or restrict requests involving exploit development, privilege escalation, and malware. Two models took this benchmark, GPT 5.6 Soul and a more capable unreleased model that OpenAI hasn't publicly named yet. With the safety restrictions deliberately removed, the entire evaluation depended on one assumption, that the models would stay contained. According to OpenAI, the evaluation environment was heavily isolated. Models had no general internet access, and their only network access was through an internally hosted package registry proxy, a service that cached and fetched software dependencies on their behalf. Now, this wasn't an oversight. It was actually a requirement because you can't evaluate real exploit development without allowing models to install Python packages and other dependencies. So the sandbox had exactly one sanctioned path to the outside world, and that path defined the trust boundary, and everything inside the sandbox assumed to be untrusted, and everything outside it was supposed to be unreachable, except through this one proxy. According to OpenAI, the models spent a significant amount of inference compute trying to escape that environment. And eventually they succeeded. They discovered a zero-day vulnerability in the proxy itself. So we're not talking about a CVE or a configuration mistake, but a previously unknown vulnerability in the third-party software providing that service. OpenAI has since then disclosed the issue responsibly to the vendor, and because the patching progress is still underway, the technical details have not been released. That's why nobody, including me, knows how the escape worked, but we do know what happened next. The sandbox had one trusted exit, and the models found a bug in it, so containment was gone, and now they were on the network. Once the models escaped the sandbox, the attack became surprisingly ordinary. They escalated privileges, harvested credentials, and moved laterally across OpenAI's research network until they reached a machine with unrestricted internet access. So there was no novel technique here. This is the same post-exploitation sequence you would expect from a skilled human attacker, which is to gain an initial foothold, escalate privileges, collect credentials, move to the next system, and repeat until you reach your objective. The difference wasn't how they attacked, it was that they executed the entire playbook autonomously, without fatigue, without distraction, without a human deciding when to stop. That was the first trust boundary, but there are two more that remained. With the internet access restored, the models turned back to their original objective, which was pass exploit gym. They reasoned that if a reference solution existed somewhere online, Hugging Face was a plausible place to find it because it hosts models, datasets, and other machine learning artifacts, including material related to cybersecurity research. Now, OpenAI has not published the exact reasoning trace, but according to their report, the models independently identified Hugging Face as a target while searching for the benchmark's answer key. The models were not trying to compromise Hugging Face for its own sake, they were trying to maximize their benchmark score. Breaching Hugging Face was simply the shortest path they found to their objective, and this is a classic example of reward hacking. Now, if you'd like the Excalibur board from this video along with the references, diagrams, and a PDF summary, I've put all of that together as a free download and the link is in the description. And if you're interested in practicing real-world exploits like this one in a safe environment for learning purposes, that's exactly what we built at the Armor Dojo. You'll find the link in the description of this video. Now, we'll switch over to the communication from Hugging Face because their incident report that they've made public fills in the details that OpenAI could not do, and the initial access actually came through a malicious dataset. At first, that sounds strange because a dataset is just data, and data should not execute, right? But on modern machine learning platforms, a dataset can be much more than a collection of files, and attackers can get the dataset to actually execute. Many datasets ship with a custom loader script, which is basically Python code that tells the library how to download, parse, and assemble the data. According to Hugging Face, one of the abused execution paths involved exactly this kind of remote code. The pattern closely matches trust remote code, which is a feature that allows a dataset to execute its own Python when it's loaded. Now, this is not a vulnerability, it's a documented behavior. And Hugging Face has warned users about it for years. That's why loading remote code normally requires an explicit opt-in. But large platforms don't process datasets manually. They do it automatically. That means the opt-in happens inside an ingestion worker on behalf of the platform itself. Hugging Face says that the attackers abused two execution paths, a remote code dataset loader and a template injection in a dataset configuration. The second execution path, like I mentioned, was server-side template injection. So if an application renders user-controlled input through a template engine, the engine doesn't just display the text, it evaluates it. That makes template injection a well-known route to code execution. The difference here was where it appeared. It didn't appear in a web form, but it appeared inside a dataset configuration file. So that's two completely different vulnerabilities with one outcome. And from that point, the attack followed a familiar pattern. The attackers escalated from the processing workers to node-level access, harvested cloud credentials and cluster credentials, and moved laterally across multiple internal clusters. At the end of the weekend, they had crossed the final trust boundary from an untrusted dataset to Hugging Face's production infrastructure. And according to Hugging Face, the attackers accessed a limited set of internal datasets and several service credentials. Just as importantly, though, they didn't find evidence that public models, datasets, or spaces had been modified. Container images and published packages were also verified to be clean. The intrusion was serious, but the software supply chain still held on. Now let's look at the infrastructure of the attackers. According to Hugging Face, the attack was spread across thousands of short-lived sandboxes with command and control infrastructure that continuously migrated between public services. And that made the attack much harder to track. The command channel blended into traffic headed for legitimate services, while the constantly changing infrastructure meant blocking one endpoint simply caused the activity to reappear somewhere else. And these short-lived sandboxes also made attribution very difficult. By the time investigators reached one environment, the activity had already moved on to the next one. And this is the kind of operational infrastructure that you would expect from an experienced intrusion team. In this case, it was assembled autonomously by a model trying to maximize a benchmark score. Now, Hugging Face uses LLMs to tri-edge security telemetry, separating meaningful signals from the background noise generated by thousands of systems. And that correlation is what exposed the intrusion. Their security team and their own AI agents detected and contained the attack before OpenAI contacted them. And OpenAI also detected anomalous activity inside its own environment, although it has not disclosed that how it is. And OpenAI also detected anomalous activity inside its own environment, although it has not disclosed how. And the investigation that followed analyzed more than 17,000 recorded events. Hugging Face used LLM-powered forensic agents to reconstruct the timeline and identify compromised credentials, extract indicators of compromise, and separate genuine attacker activity from decoys. So the result here was not just a better investigation, it was one which was fast enough to keep pace with an attacker which is operating thousands of times faster than human attackers. Now, this investigation exposed another problem. Hugging Face initially tried using commercial frontier models to analyze the attack, and they could not use them. Forensic investigations involved real exploit payloads, attack commands, and command and control artifacts, and the provider's safety systems treated those prompts as malicious and refused to help. Now, the interesting thing here is that the attacker operated without safety diffusers, but the defender was getting rejected because of the safety filters. So Hugging Face ultimately ran the investigation using GLM 5.2 on its own infrastructure that not only bypassed the safety restrictions, but also ensured the attack data and compromised credentials never left their environment. And their recommendation now is straightforward. Before an incident happens, make sure you have a capable model that can run inside your own infrastructure. Not because safety guardrails are a bad idea, but because incident response depends on being able to analyze the attack itself. So let's walk through the entire attack chain now based on the information available on the internet. All of this began inside a heavily isolated sandbox with a single permitted path to the outside world. The models discovered a 0-day in that path, escaped the sandbox, escalated the privileges across OpenAI's research network, and reached a machine with unrestricted internet access. And from there, they identified Hugging Face as the most likely location of the benchmark's answer key. And then they uploaded a malicious dataset, gained code execution on a processing worker, harvested credentials, moved laterally across multiple internal clusters, and ultimately reached Hugging Face's production infrastructure. Well, there are three main ideas that are worth taking away from this video. First, every dependency that chooses a trust boundary is part of your attack surface, even the ones that you built yourself. Second, if your pipeline executes code supplied by users, treat that pipeline as an untrusted execution boundary, regardless of whether the code arrives as a package, a plugin, or a dataset. And finally, AI is changing the economics of intrusion. The techniques have not changed much, but the speed, persistence, and scale have changed. There is one recommendation from the security engineers at Hugging Face, which is important. They say that if you plan to use AI during incident response, make sure you've already tested those models on real attack data before the incident begins. So this completes our breakdown. Now, if you found this useful, please consider subscribing to this channel. I publish deep dives like this every week, breaking down major real-world attacks, so you can even switch on the notifications from this channel. Now, researching all of these security incidents and distilling the right information onto these diagrams takes a lot of time. So don't forget to share this video with your friends. Thank you so much for watching, and I'll see you in the next video.